All right, so the second type of contact that we're gonna consider here is the rolling contact. We said that the difference, or basically the main difference between rolling contact and direct contact, in the direct contact there should be a relative movement between the two objects that they already in contact, and this relative movement, it won't gonna be achieved unless there is a sliding. It means that there is one object that slides with respect to the other one. Well, it doesn't matter whatever the two objects both are moving, or one is stationary or fixed. In either ways, you should have one slides with respect to the other one. There should be a relative movement due to slippage or sliding. But in the rolling contact, we will find a roller. Mainly, we're gonna have like an object, and this object is gonna be a roller that is going to rotate without any slipping. This is the key condition here, that there is no sliding over the surface of another object of the mechanism. The other object, it would be fixed or stationary, or it would be movable. It doesn't matter anyway. We do have a roller that rolls over the surface, like this case. We do have, this is the follower, and the end of this follower, there is a roller. This roller is going to rotate over this cam, and the cam, it has a circular profile, but it would be any other cam. I probably may have a cam like this one. Anyway, this type of problem, it is still a rolling contact problem. We do have a follower, and there is a roller that rolls over another object. The other object would be rotating, like the case of the cam. The cam is already rotating, the follower is going to rotate, the roller itself is going to rotate because of the rotation of the cam. But the key condition is that there is no sliding between the two objects. If we try to solve, there is a problem or a challenge of doing position velocity, and especially the acceleration analysis of rolling contact problem. Why? Because if we try to solve the rolling contact problem as rolling, if we decided to deal with it like a roller, and we consider the geometrical feature of the roller itself, we can only solve this problem for the velocity, but it will be difficult to be solved in the acceleration analysis. It is difficult to do acceleration analysis for this problem, so that's why it is not preferred to deal with the rolling contact problem as a rolling contact problem. It is recommended to convert a rolling contact problem into an equivalent direct contact problem. We didn't face any problem with the direct contact type of problems up there. It means that we can do position analysis, we can do velocity and acceleration analysis, no problem. But for the rolling contact problem, if we try to do acceleration analysis for the problem as a rolling contact problem, that we consider the roller itself and its geometry, and we consider or we handle the problem or treat the problem as a pure rolling contact problem, we're gonna find it is difficult for us to solve this problem, especially for the graphical part. Why? I'm gonna give you an example of something here. If we consider this is the rolling contact, the thing on the left, this is gonna be the rolling contact. So this is the rolling contact problem. Okay, this is the original problem. Again, we do have a follower. At the end of this follower, there is a roller, number 3, and the follower is number 4, and we do have the cam, which is number 2. The cam, it shall be rotating about point A, and the follower is going to rotate about this point. Let us give it a name like point O or whatever, or like point O. And we do have this C, which is the center point of this curvature, where this row, this is the radius of the curvature over which this point B shall be moving. This is like a virtual path. It is not a fixed path. This is the path of point, this is the path of point P, which is the pivot point of the roller itself. If we decided to work on this problem as a rolling contact problem, so first of all, what we're gonna do, I'm going to connect this is the point B. I'm going to connect point B, which is the center point of the roller, to the center point of the cam, and I'm gonna set up a position vector between them. Then there is another position vector of A to C, which gives the rotation of the cam. This is gonna give us like R2. This R2, its time derivative twice, is gonna give us the velocity and the acceleration components of the cam itself. It means that R2, it defined the cam, and R4, this defined the follower itself. This is the R4 vector that it will be set up between the point P and point O. And this makes sense because we do have this follower with a fixed length as R4, and this point B with respect to is a fixed distance, but theta 4 is going to change. The same thing for R2, theta 2 is going to change, but the distance between A and C is a fixed distance because anyway it will be provided, it will be given to us. Then we have to close the loop, and then we're gonna connect point C to point P, and then we're gonna close the loop, and let us assume that this is like R3, where this R3, it's gonna work not physically to the roller itself, but this is just a connecting virtual link that connect these 2 points, point B and C together, in addition to another virtual link, which is gonna be R1 just to close the loop. This R1, it will be set up between point O and A. If we try to investigate these different position vectors of this mechanism, there in the direct contact problem, we said that in case that we have a cam and there is a follower, your objective is just to connect the point of rotation to the sliding point, or the point of contact over which there is a sliding. Here, the point of contact is this one. The point of contact between the roller and the cam is this one. This point, there is no sliding at this point. This point has zero velocity and zero, but it has a component of the acceleration, but it has a zero velocity. Why? Because it is a fixed point with respect to the roller, right? So it means that this is the point of rotation because for the roller itself. Why? Because simply this point, there is no sliding at this point. So I cannot connect this point to the point of contact here. Then this would be another option. I can connect even this point A to this point, then the point of contact, then I'm gonna connect here, then you're gonna end up with a loop. Make sense? So it means that we can set up different loops for this problem, or different position vectors for this problem. One of the loops basically is this one. If we try to solve this loop, which is R1, R2, R3, and R4, and I ask you to define which one of these are constants, which one is variables. So you're gonna realize that R1, theta 1, definitely both are constants, right? Agree? Why? It had been set up between two fixed points, point O and A. And R2 is gonna be constant, but theta 2 is variable, right? Why? Because simply this angle is going to change if we give rotation to the cam, but this distance between A and C is a fixed point, is a fixed distance. But how about R3? R3 is gonna be constant. Why? Because this distance between point C and point P is a fixed distance. This all the time equals rho. So simply R3 is gonna be equal to rho and is gonna be constant all the time, right? As we did before in the contact problem, because this distance, point B, is located over the circumference of this curved path of point B, and this curvature or this curved path, it has a center point C, which is this point C, which in this case just the center of the cam, but it is not necessary to be all the time the center of the cam, because basically this point C stands for the center of this curvature, which is with a radius of curvature as rho. So R3 is going to be rho and it's going to be constant, but theta 3 definitely is going to be variable. Why? Because simply theta 3 is going to be, in this case, theta 3 is going to be variable. Why variable? Because simply this R3 is going to rotate as the cam rotates. How about R4? R4 as a magnitude, it is constant, but the theta 4 is variable. So R4, it is constant, but theta 4 is variable. So having a look to all of these different parameters, you aren't gonna find any. This is a constant vector, so there is no velocity, there is no acceleration for this R1. R2, it has velocity and acceleration component, but there is no carriers acceleration for this one, because both R and theta, both of them are not variable. Just one is variable, which is theta. 2. R3 the same. R3 has no carrier acceleration, and R4 there is no carrier acceleration for R4. It means that if we decided to work with the problem here as a rolling contact, there is no carrier acceleration at all in this mechanism, right? According if we decided to handle it as a rolling contact problem. But the fact is that there should be a carrier acceleration. It is typically the same like the example that we discussed above here for the case of the direct contact. For this example, we said that if we choose R1, R3, R4 in addition to R2, we're gonna end up with a loop. This loop will not secrete or provide any carrier acceleration, but in fact there should be a carrier acceleration for this mechanism. Because why? Because we have this slider is a sliding over a rotating object, and this is the second type of the direct contact problem, and we agreed that this second type should provide a carrier acceleration. How we can find this carrier acceleration? We said that we have to connect the R5. This one, and if we decided to work over this loop, which is this one, we're gonna end up with the carrier acceleration. So for this problem, for example, if we decided to work over this one, although it is a direct contact problem, right, it is not advised to work with loop R1, R2, R3, and R4. If we did so, we can only solve for the velocity, and we're gonna struggle in finding the acceleration. The acceleration, you're gonna find that the number of unknowns is higher than 2, and you won't gonna able to proceed. In addition, the formula of the loop closure equation for the acceleration analysis using the R1, R2, R3, R4, it is not possible, or it doesn't make sense, or it is not visible to this mechanism, because this mechanism should provide a carrier acceleration. So therefore, for this mechanism, we have to use the Brown loop, this one, using R1, R2, and R5. It is typically the same idea here, down here for the rolling mechanism. For this rolling mechanism, rolling contact problem, for this one, if we decided to handle this one as a rolling contact problem, you're gonna find that none of these position vectors will have both r and theta, the direction magnitude, both are variable, none of them. It means that there is no carrier acceleration, but in fact there should be a carrier acceleration for this mechanism. Why? We do have a contact or a rolling contact between two movable objects. So definitely there should be some slide, there should be some carrier acceleration for this problem. But if this cam for some reason is fixed, so definitely there is no carrier acceleration. So if you solve this problem as a rolling contact problem or even direct contact problem, you can solve this problem, I mean, using the rolling contact problem, as long as this cam is fixed, because there is no carrier acceleration. But here, if we decided to work over this problem with two movable objects, the follower in addition to the roller, in addition to the cam, everything is moving. So definitely there should be carrier acceleration that should be shown up here, as I'm gonna show you, where is the source of this carrier acceleration. So if we are interested only in the position analysis and the velocity analysis, we can handle with the problem or deal with the problem like a rolling contact problem. But if we are interested in the acceleration, we have to convert. This is the procedure. It is recommended to convert the rolling contact problem into an equivalent direct contact problem. So if this is the original, let us split it here. This is the original rolling contact problem. I'm going to convert this problem into an equivalent direct contact problem. What is the difference between direct contact and rolling contact? In rolling contact, there is a roller and there is no slipping at the mating surface or the contact surface between the roller and the other object. But in the direct contact, there should be there should be sliding motion between the two objects. So the approach is very simple. Your objective is just to specify or identify the path of the pivoted point or the center of the roller. We do have a roller here, its center point, it rotates about point P. And as this cam rotates, this point P is going to rotate over a path. This path, it will be centered at point C with a radius of curvature rho. This rho will be provided, the location of point C definitely will be provided as well. Make sense? This rho for this problem, just for this problem, It can be calculated. You can calculate this rho if you try to connect point C to B. This distance is going to be the radius of the roller plus the radius of the cam, just for this problem, but this is not all the time. Anyway, there should be some data provided on the rho, the radius of the curvature of point B. Like you're gonna assume that there is a virtual path. This virtual path, you have to locate this one for point B, and then you are going to replace this roller by a slider that slides over a curved path. So we already resetting back again to the thing that we did before as a direct contact. This is an equivalent direct contact. To replace the roller with a slider of its center point or its point of rotation, this is gonna give us, this is simply how we can convert the rolling contact problem, the original one, into an equivalent direct contact problem. So, and this is what I've did here. There should be a roller here, and this is the point T, which is the center point of the roller. What we did here, we replaced the roller with a slider. And this is the point B, and this is the path over which point B is already moving. So you're gonna consider, in this case, we're just gonna consider that we do have a slider that slides over a link or over a curved path, like this case. Make sense? This is how it works for this mechanism. And now we're gonna solve this one. This is a direct contact problem. This one is a direct contact problem. Why? We do have a slider that slides over a surface. This is the surface, right? But the key idea here that this surface, it is not fixed surface. This surface is movable. It moves. Why? Because this surface is already belong to the cam, and the cam itself is going to rotate. So if we do have a direct contact problem like this one, simply your objective is just to locate, as we did above before for the direct contact, to locate the point of contact, which it should be point B. And then you're gonna connect the point of contact to the fixed point. This is gonna give us R. This should be the R4 for the follower. And if you connect the fixed point to the other fixed point in the mechanism, because we do have the cam rotates about point A. So if you connect this point B or point of contact to the fixed point of the other object, this is gonna give us the R2. This R2 defines the velocity and the acceleration for the cam, and R4 defines the velocity and acceleration for the slider, or the follower, I'm sorry, for the follower. And if you, this is gonna give us like open loop. If we try to close the loop, we have to connect these two fixed points with R1 as already given here. This is gonna give us this loop. Then we can solve this loop. But remember that R2 in this mechanism define its time derivatives, gives the velocity and the acceleration of the cam. R4 gives the velocity and acceleration of the follower itself. But how about the slider? Physically, there is no slider. This is our transformation. This is our assumption, right? There is no physical slider there. But there is a roller. If we are interested in the angular velocity of the roller or any other things, we have to work on the other loop, this small loop with R5 and R6. So it means that if there is something is required regarding the roller, we have to work over another loop, which is the second loop here that already include as R2 as a comment between these two loops. But the main loop that should be solved, basically, it should be the first loop, which is this one, R1, R2, and R4. If we decided to study these R1 and theta 1, definitely both are constants, while they already set up between two fixed points. But how about R2? R2, it's gonna be variable. R2 is gonna be variable. Why variable? Because this distance between point P and point of rotation is going to increase and decrease depending on the rotation of the cam. Assume that this cam has been rotated all the way to the right. So this distance becomes shorter. If this cam rotates to the, if it rotates to the left, this distance becomes shorter. If it moves to the right, it becomes longer, and so on. So anyway, this means that theta 2 is already, R2 is already variable. Definitely theta 2 is variable. We can understand this, right? Why? Because this one is rotating, and R4 is gonna be constant. as we discussed before, that this point B is going to be a fixed point with respect to the follower, but it's going to be changeable point with respect to the cam, right? It means that the distance between O and B is going to be fixed distance with respect to the follower, which is R4. It means that R4 is constant, but theta 4 definitely is going to be variable. Why? Because this follower is going to rotate. As you can see, we end up here with a position vector with both r and theta, both are variables. This indicates that we're gonna end up with a Carrier acceleration, and this makes sense. So this means that in the original mechanism, there should be a Carrier acceleration, but it won't gonna show up unless we treat this problem like a direct contact problem. If we try to work over this problem, simply if you connect this link, which should be like the R2 here, this link in this case, it is variable in terms of magnitude and direction. It means that this point with point P, with respect to point A, it has three components of the acceleration. One is tangential, one is normal, one is a Carrier acceleration. But this Carrier acceleration, it won't gonna show up for this mechanism if we treated it as a rolling contact problem. But if we converted it into an equivalent direct contact problem, we can secrete or end up with this Carrier acceleration. Make sense? But simply if we are just interested in the velocities, or we don't care about the velocity or the acceleration of point B with respect to point A, we can even deal with the problem like a rolling contact problem. Make sense? And since we're already interested in the complete kinematic analysis of the mechanism, so this means that all the time we're gonna convert the rolling contact problem into an equivalent direct contact, and the direct contact problem is the one that is gonna be solved. So this indicates that in general, we have two different types of contacts. We have rolling and direct. Anyway, the rolling, we're gonna convert it into direct contact. So it means that you have to study only one type of contact, which is the direct contact problem. Make sense? So also this is very similar to this case. If we do have this follower and this is a roller and this is the cam itself, this is the cam, and this is another problem, like you do have a follower and roller. Whatever the roller is already located over this curvature or over this straight surface here. In either ways, your objective is just to locate the path of the point of the center of rotation of the roller, like this point P. This point P, its path is gonna be this path with a radius of curvature rho. But in this case, it's gonna have the path of point B is gonna be this line. With this line, it has a radius of curvature that tends to infinity, but here the radius of curvature, it will have a value, a specific value. Once you specify this one, this is the rolling contact problem. This is the rolling contact problem. You're gonna convert it into an equivalent direct contact problem, and this is the one that is gonna be solved, right? So simply, if we already consider this first follower, simply we're gonna replace this one with a slider that slides over a curvature, over a curved surface, like this one. This is the slider, and this is the follower, and this is the curved. So simply, what we're gonna do, we're gonna set up some position vectors. One position vector that is going to be set up between the fixed point of the cam, or the point of rotation of the cam, to the contact point, which is point P, and the same thing for the follower from the fixed point or its point of rotation to the contact point. This is gonna give us like R1, R2, and R4. Then we're gonna set up R1 to close the loop, and this is gonna be the loop that it should be solved. As you can see, R1 it is constant, and for this case, R1, theta 1 are constants. Both are constant, or we can write them down here. R1, theta 1, both are constants, right? And R2, theta 2, both of them are variables. That's why we're gonna end up with Carrier acceleration. Both are variables. Why? Because the distance between P and the center of rotation is going to change. For example, if you give rotation to the cam in any direction, this distance is going to change. And R4 is gonna be, the magnitude is gonna be constant, but theta 4 itself, it's gonna be variable. So that's why we're gonna end up here with a careless acceleration if we treated this one. The same thing applies to the other one. Here, the slider is going to slide. This is typically the same like a link, and there is a slider that slides over a surface, but this surface is a movable surface, right? So what we're gonna do, we're just gonna connect the point P with the contact point to the point of rotation of the first object, which is the cam, to the point of rotation of the second object, which is the follower. So we're gonna have R4 and R2, then we're gonna close the loop with the R1. This is gonna give us this loop. Then your objective is just to solve this mechanism. As you can see, R1 is constant in terms of magnitude and direction. R4, it is with constant magnitude but variable or changing or time dependent direction, but R2, it has both R and theta are variable, and that's why even for this case we're gonna end up with a careless acceleration. Make sense? So this is for this mechanism. Also we do have another one, or these two different mechanisms, they are very similar. Here we do have a crank slider, but instead of having crank slider mechanism, we do have crank roller mechanism. We do have, this is the crank, and this is a connecting rod, and this is a roller that moves over a straight surface or even over a curved surface like this case. So this is a rolling contact problem. We can convert this one into an equivalent direct contact problem. How? Simply, you just gonna replace this roller with a slider here. This is the path, this is the center point of the slider, and you're just gonna consider this slider is already sliding over this inclined surface. So this is a direct contact problem. This is the equivalent one. We converted the roller, replaced the roller with a slider at point C. Then you're gonna set up this different position vector. We'd have R2 for the crank, R3 for the connecting rod, and we should have a short R4 for the slider going in the same direction of motion of the slider, because this is a straight surface as we did many times before, even before today's lecture, and we do have the R1 to close the loop, right? So this is gonna give us the loop, and as you can see, for this mechanism, R2, for this mechanism, we're gonna have R2 is constant, but theta 2 is variable, right? And R3 is constant, theta 3 is variable, and R1, theta 1, both are constants, but R4, for this mechanism, R4 is variable, but theta 4 is constant, right? So there is no careless acceleration. It means that even if we treated this problem as a rolling contact problem, we can solve this problem as a rolling contact problem because simply we don't have any careless acceleration. How we can do so? For example, one of the things that we can set up R2 for this mechanism and R3 for this link as a vector, and for the roller itself we can assume that we have, this is point C, and we're gonna have another point here between point C and the point of contact. We're gonna have a position vector as R4, and you should understand that this R4, it is not necessary to be over the same line as R3. No, they are two different position vectors. Then you're gonna close this one with R1. But probably in this case, the number of unknowns will be more than 2, so you have to break it down, and it would be somehow complicated, even more complicated than if you treated it as a direct contact problem. But we can solve it as a rolling contact since there is no careless acceleration, but it's gonna be somehow challenging. So that's why all the time it is recommended, in case that you have a rolling contact problem, is to convert it into an equivalent direct contact problem as I did here. The same thing applies to this problem. Replace the roller with a slider that slides over this curve, and you're gonna end up with these different loops. So we're gonna have R2, R3, then there should be an R for this slider, but the slider moves over a curved surface. So we said that to define R for the slider, we should connect the center point of rotation of the curve, the center of the curvature, to the slider itself. Then this point is going to be connected to another fixed point, and this point C is gonna be fixed point. That's why it will be located, it will be given to us where is the center point of the curvature of this slider. So it means that the location of this point will be given. This will be given its location, and this point, it is a fixed point. fixed point. Make sense? So this is the key idea of the rolling contact problem, is again to convert the problem into an equivalent direct contact problem, and then you're gonna treat the problem as a direct contact as we did before in the start of this video. What I'm gonna do right now, I'm gonna give you this example. I'm gonna show you how we can solve this example of the rolling contact. First, we're gonna convert it into an equivalent direct contact problem. Then I'm gonna show you how we can set up the equations, the different position vectors, the directions and magnitudes of these position vectors, then how we can form the loop closure equation, and definitely the rest of the problem is gonna be formal, like as we did many times before for the complex algebraic method. So in this example, it is given that we do have this cam, which is a disk cam, has the shape of a disk, and there is a roller as a follower. So this is commonly known as roller follower, and this is the link PB that connects the roller, and the point of rotation of the roller is going to be point P, and the roller is already rotating with no slipping or with no sliding over the surface of the cam as the cam rotates. And the cam rotates with an angular velocity that is given by 12 revolutions per minute, RPM. To convert from RPM to radian per second, you're gonna multiply times 2 pi over 60. It means that the equivalent omega 2 is gonna be 12 times 2 pi over 60 to convert from RPM to radian per second. So it's gonna be something in terms of radian per second, and its direction is already given in counterclockwise direction. Also, it was given as constant, but constant, it means that alpha 2 is already 0, but in some cases omega alpha 2 would be provided. If in the general case, it means that we do have angular acceleration of this cam. And in addition, there are some given dimensions here in terms of this angle 135 degrees. This is the current orientation or the current position of or direction of this cam, and we have the 35 millimeter, which is the distance between point A and C, in addition to the length. The length of this link is already provided by 87.5, in addition to these two dimensions, 75 horizontal and vertical dimensions of these different elements. The cam was given a number as 2, the roller as 3, and the follower as 4, and definitely one is going to be the ground, right? Again, it is required to do a complete position analysis, velocity and acceleration analysis for this mechanism, and find some of the velocity components, whatever for point P and point C, whatever the requirements in terms of velocity and acceleration. Anyway, there is essential or arbitrary loop that we have to assume or consider for this mechanism. This is a rolling contact problem. We have to convert it into an equivalent direct contact problem so we can handle this problem. So how we can do this? The key idea is to identify the point of rotation of the roller, and then identify the path over which this point B is going to rotate, as the cam itself is going to have a rotation. So as the cam rotates, this point B is going to rotate over a circular path. This circular path is going to be, as I'm representing it here, as a dashed line. This dashed line represents the path of point P. So we can say that this is the path of point P. Make sense? Then what? Your objective is just to do some connections here, just connect some things together or set up the loop as a direct contact. To convert this one into direct contact, simply I can replace the roller by a slider. So I'm going to assume that there is a slider, and this slider is going to slide over this curved path. And this curved path, it has a center point, which is this point C, and it has a radius of curvature as rho. So how much is rho? This is essential to calculate this rho value. Simply, this rho should be the distance between point P and point C. If you connected this distance, these two distances together, how long is this line? This line is going to be the radius of this big circle, because this is the center point of the same circle, of this circle. And in the meanwhile, this is the center point of the curvature or the curved path of point P, plus the radius of the roller itself. The radius of of this big circle is already provided by how much? Yeah, it should be given. Yeah, it is given here by 50 millimeters. This is the radius of the big circle, plus the radius of the 12.5, which is the radius of the ruler. So we're gonna conclude that rho, which is the radius of this curvature, is gonna be the 50 plus 12.5. You can calculate this one as 62.5 millimeter. You should understand this is not necessary to be the case all the time. This is just for this problem. For this problem, if we try to calculate this distance, we're gonna end up with 50 plus 12.5, which is gonna give us the 62.5 as the radius of the curvature, right? Then we're gonna end up with a problem, very simple problem, that we do have this roller, this slider. We do have this slider that slides over this curved path. Make sense? So as we defined before, this is a direct contact problem. We have to set up some position vectors, right? The first position vector is gonna be between the point of rotation of the cam to the contact point, which is point P. This is gonna give us R2. Why 2? Because this is the cam is given number as 2. Then we'd have another position vector that should be set up between point B and point P, which is the contact point and the fixed point or the point of rotation of the follower. This is gonna give us R4. Why 4? Because here this is R4 for the follower number 4. Then this is open loop. To close the loop, we have to connect these 2 points, points A and B, with R1 vector. Make sense? So this is gonna give us the R1 vector. Then we're gonna end up with this loop. Then this loop can be simply solved as position, velocity, and acceleration analysis. But we have to set up this loop in terms of R1, how much it is, how much is R2, R4, in terms of values, in terms of directions, which ones are constants, which one are variable. So this is the mechanism, and this is the equivalent mechanism here in the direct contact, because this simply should be the roller here of this mechanism. So we set up R2, we set up R4 and R1, right? So if I ask you how much is R1, how much is theta 1, which one is variable, which one is constant, the same thing for R2 and theta 2. How about R3, or there is no R3, R4 and theta 4. So R1 and R2 should be the distance between these 2 points, point A and point B, right? Which it should be this point B. This distance, since there is a fixed distance, because it is set up between 2 fixed points, so R1 we can do trigonometric calculation to come up with a value for R1. No problem with this one, because definitely it should be given. Any fixed point, their location should be provided to us in the problem. So simply, if we consider this triangular shape, this one, this height is already given by 75. This resultant distance was given by 75 millimeter in the original problem up there, as already given here. If you just connect this line and this line, this is gonna give us this triangular shape, right? Where this distance is 75, this vertical distance is already given by 75 here. All right? So simply R1 is gonna be the square root of, or the hypotenuse of this 90-degree triangular shape. To end up with R1 definitely is gonna be 75 square root of 2. This is the value in terms of millimeter, and definitely it should be constant value. Why constant? Because this is a constant distance. How about theta 1? Theta 1 is already given here, it is 45 degrees, because from the start point, if you draw a line to the right, rotate counterclockwise, this is gonna give us the theta 1. Theta 1 definitely is gonna be 45 degrees, and again, it's gonna be a constant value. This is for R1. How about R2? R2 should be the distance between point A to point P. We have no clue how much it is, and even it is not given. So it means that this should be one of the unknowns for now, for the instant of time. It should be one of the unknown, and it should be variable, as we discussed or as we agreed before, that this distance, as this point P is going to move over this curved path, the distance between P and A is going to change. It means that this R2 is going to be variable. Theta 2, it's going to be theta 2, which it should be this angle. This angle theta 2, it should be the angle between, if you draw a line from the right, rotate counterclockwise, this should give us the theta 2, which it should be this angle. But remember that there is an angle that is already provided to us here, which is the 135 degrees, this angle. Up there is already given, this 135 degree. Theta 2, it should be this angle. So if there is any kind of relation that we can find of theta 2 in terms of the 135 degrees, yes, we can. This indicates that theta 2 is already given. But initially in the beginning, even if you decided that I have no clue how much is theta 2, and even initially, let us assume that theta 2 is unknown. So this is going to be the second unknown to us for this problem, right? And theta 2 definitely is going to be variable. Then how about R2? R2 should be the distance between point P and B, which is already given up there by the 87.5 millimeter, which is this distance. So R4, it is already given that it is fixed constant value, millimeter, and it should be constant, which it should be the length of this length, And this theta 4 is going to be variable definitely because this length is going to rotate, but we have no clue how much it is. Make sense? So if we consider that theta 4 is already unknown. Anyway, it is not given, theta 4. And we do have R2 is unknown in addition to theta 2, as we mentioned, it should be unknown, right? But in this case, if we consider theta 2 is unknown, in this case, we're going to end up with 3 unknowns. So we're going to be able to proceed further, right? But definitely, if you just observe theta 2 is already given, because there is one given information that we didn't use, which is this angle 135. This angle is already defined for the cam itself. It means that this angle defines the direction of the cam. And it means that, and the thing that we define for the cam is R2, and theta 2 is the thing that it should be used to define the direction of the cam. It means that the 135, it is related somehow to the theta 2 that we have to use in this problem. So your objective is just to calculate theta 2 for this problem, how much it is. Make sense? So we can do some trigonometric calculations to end up or to find theta 2, or you can simply, so one of the options, basically, the thing that you should understand, that theta 2 it is indirectly given. You can do some trigonometric calculations, and it is acceptable to do this trigonometric calculation to come up with the value for theta 2, or simply you can deal with this theta 2 like another third unknown. So we do have here 3 unknowns, so we weren't gonna able to proceed. So we need more loop. We need another loop, one more loop. This one more loop, it would be set up like this loop that R5, you can connect this point A to point C with R5, and then we're gonna connect point B to point C with the R3 in this case. So we're gonna end up with a new loop, which is this one. So if you decided to work, so one of the options, as I mentioned, that since theta 2 is not given, it is not directly given, but it is indirectly given. So you can do some trigonometric calculations to come up with a value for theta 2, or if you are not interested in these trigonometry things, you can solve, you can form another loop. You could consider that theta 2 is unknown already and proceed and form another loop. So we're gonna form another 2 position vectors, R5 and R3. Then you're gonna define R3 and theta 3. Also the R5 and theta 5. So I defined these 2 extra position vectors just to give me the direction theta 2. Make sense? This is like we gonna do some trigonometric calculations, but we're gonna do it through the complex algebraic method. So R3, it should be the distance between P to C, which it should be rho, as we discussed. Our rho we calculated up there as 62.5, which is this distance. It should be rho, the sum of the two already, as we discussed before. So it means that R3 is already given by 62.5 millimeter, and this distance is a constant distance. And theta 2, it should be this angle, theta 3, I'm sorry. This theta 3, it should be this angle, which we have no clue how much it is. It is, with respect to us, this theta 3 is unknown. How about R5? R5, the distance between A and C is already given to us here by 35 millimeter. So this one is already given by 35 millimeter, but it is constant, right? And theta 5, which it should be from the start point, rotate, move to the right, rotate counterclockwise, you're gonna end up with theta 5. Theta 5 is the 135 degrees that already provided to us, but it is variable, because this cam is going to rotate. So this is gonna give us another unknown. So in total, we're gonna end up with 4 unknowns, r2, theta 2 for the same vector, and theta 4 and theta 3, right? So 4 unknowns, and we can form 2 loops. We are in a good shape, right? Because each loop, we are limited for just 2 unknowns. It means that 4 unknowns, we need 2 loops to find them, right? So simply we have lots of options here. One of the loops basically is just to assume this loop, this little small loop that include R1, R5, R3, and R2 as a one loop. And the second loop is going to be this one. If we consider this first loop on the left, R2, R5, and R3 as a loop, this loop it will include 3 unknowns. So I'm going to be able to solve it. Why? Because R2, R2, theta 2 are 2 unknowns. Theta R5 it is fully defined. R3 it has another unknown which is theta 3. So if we decided to form a loop which is this small triangular shape that include just R3, R4, R5, R3, R5 and R2, this gonna give us a loop closure equation with 3 unknowns. So we're gonna able to solve it. If we decided to pick the other loop on the left, we do have R1 is fully defined, R4 it has only 1 unknown, R2 has 2 unknowns. So we're gonna end up as well if we decided to work over the loop on the left, we're gonna end up with 3 unknowns. So we're gonna able to proceed. So it is clear to us, as already given here, it is very clear that the problem with R2, right? It means that I have to exclude R2 and we're gonna consider this big loop that include R1, R5, R3, and R4 as a one loop. Then I'm gonna solve this loop. This loop will include only 2 unknowns, theta 4 and theta 3. R5 is fully defined, R1 is fully defined. So we're gonna end up with a loop in 2 only unknowns. Then once we find these 2 unknowns, which are the theta 3 and theta 4, we can simply solve any one of these 2 unknowns for the R2. But remember that the main unknown that we are seeking basically is theta is R2. R2, this is the main position vector that we are seeking, because once you define this R2, which had been set up between the point B and the point of rotation, it means that to find R2 and theta 2, this is the main concern in terms of, or the main objective in terms of position analysis. Their derivatives also gonna give us the velocity component of the same position vector and the acceleration, and this is what we are seeking mostly. So it means that we have to work over 2 steps or 2 different loops. The first loop, which is the big loop, which we're gonna give it a name like loop 1, then we're gonna consider any one of these 2 loops, like the loop on the right, for example, to be solved second. So we're gonna solve loop 1 first. So we're gonna start here with the position analysis. In this position analysis, we do have 2 loops. So we're gonna start with loop 1. The first loop includes 4 position vectors, R1, R4, R3, R5, just exclude R2. So we're gonna have, and as you can see, R5 and R3, they already rotating in the same direction, but R1 and R4 in the opposite direction. So we can say that R1 vector plus R4 vector in one direction equal to the R5 vector plus the R3 vector in the opposite direction. R1 it is fully defined, R5 it is fully defined, but this one has magnitude no direction, so this is case 4, right? 2 unknowns direction for this 4-bar linkage or this 4 position vector. So what we're gonna do again, do as we did before, collect all the unknowns on one side, then solve and proceed. With the case 4, your objective is just to find theta 3 and theta 4. When we solve this one, we're gonna end up with theta 3, we're gonna find it by the 65.4 degrees, and theta 4, we're gonna find it by the, how much it is? Yeah, 160.8 degrees. This is for the first loop. So we got theta 3, we got theta 4, now we still have two unknowns. These two unknowns belong to the R2, so we have to consider R2 in any one of these two loops. The loop on the right or the left, it's up to you. It is commonly to use the loop on the right. This is the main loop that we are needing because we are interested in the angular velocity and acceleration of this follower, definitely. So now we're gonna move to the second loop, loop 2. For the second loop, we do have here R2, R1 and R4 going in the same direction, but R2 in an opposite direction. So we're gonna have here R2 as a vector. It is fully unknown, equal the R1 vector plus R4 vector. Now R4 it is fully defined, R1 it is fully defined. Why? We already got theta 4 and R4 was already given up there by 87.5. So it means that we can solve this loop for the R2 and theta 2. Solving for R2, theta 2, we're gonna find them by the R2, we're gonna get it by 104 millimeter, and theta 2, and remember that this is variable, and theta 2 we're gonna find it by the 94.2 degrees. This is for R2 and theta 2, and this is the position analysis. But there are some procedures, I didn't explain them because we already explained them before for the analytical solution, but it is simply the same. This is case 1. This loop, for example, this loop causal equation, it is case 1. In case 1, simply you rewrite again into exponential form, then you're going to split it into real and imaginary parts, then you're going to form the tangent of theta 2 to find it with this value, then you're going to plug into any one of the two real or imaginary equations, you're going to end up with the magnitude of R2. The same, this is case 4, so we can simply do the position analysis, typically the same as we did before. Then after that, we have to do time derivatives, right, of the equations. But which equation that we have to do time derivative for is this one. This is the main equation that we needed. This one. It means that you aren't gonna do any time derivative to this equation. We just use this equation to do to skip the trigonometric calculations that it would be difficult for us to figure it out through this mechanism. So we applied this loop, which is loop 1, to find this theta 3 and theta 4, so we could find the theta 2 and R2 for the position vector number 2. Now, for the velocity analysis and acceleration analysis, so 2 and 3, which are the velocity and acceleration analyses, what you're gonna do, you're just gonna do time derivative of this equation, which is R2 EI theta 2 plus the R1 EI theta 1 plus the R4 EI theta 4. You should understand that this term, its time derivative is going to be 0. Why? R1 and theta 1 are constants. R4 is constant, theta 4 is variable, as we defined up there, right? Theta 4 is variable, theta R4 is constant, but R2, theta 2 both are variable. So the time derivative of this equation, to find the velocity, this R is variable, so this is going to give us R dot EI theta dot plus the R2 theta 2 dot EI theta 2 plus pi over 2, as we did many times in the analytical solution. This time derivative will be 0, but here R4 is constant. This is going to give us theta 4 dot, which it should be omega 4, the angular velocity of the link number 4, I theta 4 plus pi over 2. This is going to give us the velocity equation. Let us give it a name like equation 2. And then we're going to split it into real and imaginary parts. You should understand that omega 2 is already given. Omega 2 is already given constant by the 12 times 2 pi over 60 to convert to radian per second, as we did above. R2, this should be like the virtual sliding velocity of the slider, because there should be a slider up here, right? So this slider is going to slide in the vertical direction that is parallel to the R2, right? And this explains why R2 is going to increase or decrease. It means that there is a sliding velocity of a virtual slider over with respect to this point B. It means that this is like we do have like two different sliders. One is parallel to the R2 and one is perpendicular to the R2. Like this is the normal or radial direction, and this is like the tangential component over this curve. But we're gonna go through these details. For this one, simply we do have R2 dot, which is shortly related. We said that R2 it means V. It means that this is sliding velocity related to the virtual slider that replaces the roller itself. Definitely this R dot will be unknown. Theta dot, which it should be omega 4, also it is unknown. So we're gonna end up with one equation, or this loop correlation equation has two unknowns that is going to be split into real and imaginary parts. So you're going to end up with two equations. Then simply you can solve them for R2 dot and theta 4 dot. Then if we did derivative one more time to this equation, we're going to end up with the acceleration. And here we shall end up with a curious acceleration. If we did time derivative, R2 dot is variable, theta 2 is variable. So we're going to have here R2 double dot EI theta 2 plus the R2 dot theta 2 dot EI theta 2 plus pi over 2. This is the time derivative of this term. It had been split into two terms because there is a derivative of multiplication of two functions, plus the R2 is variable. So R2 dot theta 2 dot EI theta 2 plus pi over 2. And there is another term, other two terms basically. So plus the R2 theta 2 double dot EI theta 2 plus pi over 2, and we do have here the theta 2. So this is going to give us R theta 2 dot square R2 theta 2 dot square EI theta plus pi, and this is going to be the normal component of the acceleration. So it has been split over three components, equals the R4 is just constant. So this is going to give us the R4 theta 4 double dot EI. Well, let us move here, equals the R4 theta 4 double dot square EI theta 4 plus pi. This is the normal component, plus the R4 theta 4 double dot. This is the tangential component, which is theta 4 plus pi over 2. Then this is the curious acceleration, as we discussed many times. The R dot, theta dot, this is these two components, they're gonna be combined together to end up with the curious acceleration. This is the A curious acceleration that we discussed before. Then as you can see, we have here only two unknowns. R2 double dot is unknown, and then theta 2 double dot, it is 0. Why? Omega 2 is already, this should be alpha 2, that already given by 0. Why? Because omega 2 was constant. And here theta 4 double dot, which is should be alpha 4, it is also unknown. So we do have one loop correlation equation and just two unknown that can be solved simply. If we split it into real and imaginary parts, we're going to end up with two equations that can be simply solved for these two unknowns. And once we find them, we're going to end up with this problem, unless there are some other requirements in terms of the velocity or the acceleration. For example, if the velocity or the acceleration of point B was required, we can simply refer to point B or either point A. So we do have already, we're gonna use the R2 or R4 to find these velocities and accelerations of the point B. If we are interested in finding the velocity or acceleration of point C, we can do so by using the R5 in this case. If we are interested in the velocity or the acceleration of the contact point of the roller, which it should be this point somewhere here, we're gonna set up another position vector between this point C and this point, which it should be the same direction as R3, but with a different length, shorter than R3, just the radius of the circle as 50 millimeter. Make sense? So that's it for today. Today we have discussed two different types of contacts. And this special type of problems, it is highly important in case that we do have these direct contacts, especially over curved surfaces. Whatever the surface is moving or stationary, then we discussed the rolling contact, and we knew how we can convert the rolling contact into an equivalent direct contact so we can solve it. And this is the end of this video. Thank you, and see you in the next video.